I'm Sheetal Thekti. I'm in my second year as a PhD student at the University of Virginia, Department of Systems and Information Engineering. I have received an MSc and BSc from the University of Michigan, Department of Industrial and Operations Engineering. Today I'll be discussing my work on modeling risk and avoiding regret of adjacent land development for transportation and other infrastructure systems. This was prepared for the Society for Risk Analysis Student Merit Competition in the Engineering and Infrastructure Specialty Group. I would like to thank the Federal Highway Administration, the Virginia Department of Transportation, and the Virginia Transportation Research Council for their support and sponsorship of this study. I also thank my colleague Chen Zhao and my advisor Jim Lambert. Finally, I thank the Society for Risk Analysis for considering me for the Student Merit Competition. This 10-minute presentation in several parts explaining how this study is critical in protecting national infrastructure while avoiding regret and exorbitant cost. Consider a transportation corridor facing future land development. Land development adjacent to corridors not only leads to greater traffic along the corridors, but also requires taxpayer funding for protective measures to be taken in order to minimize congestion and loss of productivity in the area. Eventually, costly right-of-way may need to be purchased for corridor improvements. However, if proper proactive planning is not implemented, land may not be available, causing serious problems for the transportation infrastructure. These serious risks need to be studied and managed in order to avoid surprise, regret, and belated action. This problem extends across all varieties of infrastructure systems. Of the U.S. Department of Homeland Security's 17 most critical infrastructure list, some, more than others, have a geographic component. The goal of this study is to analyze a large-scale transportation network vulnerable to adjacent land development and prioritize sections of corridor for investment. An earlier approach to this work by Linthicum and Lambert was found to have particular deficiencies. This study contributes to the literature by incorporating the time domain on intervals, can easily be updated with new information, addresses geographical differences in development patterns, and considers volatile and uncertain conditions, such as climate and other environmental changes, changes in social or demographic patterns and land uses, changes in regulations, as well as many others. The adverse consequences of unexpected land development may include unnecessary congestion and inefficiencies along critical transportation corridors that may lead to lost productivity, increased fuel emissions, and loss to nearby businesses. In extreme events, the consequences can be even more severe. Corridor protection involving improved access management and capacity increases may encourage development and population growth in some areas, thereby allowing for greater efficiencies in the transportation structure. Greater economies of scale can be found in densely used areas, while increased tax revenues and employment aid entire communities. It becomes apparent that there are important trade-offs between risk and opportunity in this study. These will be quantified and evaluated in order to make the best decisions for the transportation network as a whole. Costs include cost of planning time, including salaries and overhead, right-of-way purchasing, construction or operational changes, access management, and others. The most challenging aspect of the data extraction involved the integration of quantitative and qualitative data available in widely varying scales. The Landsat National Land Cover Database offered geographical land use and land use change information. The Bureau of Economic Analysis gave us valuable employment and economic indicator data. The U.S. Census shared a wide array of socio-demographic data. The Department of Housing and Urban Development held key indicators on housing and affordability. These databases, in addition to many others, were essential for this effort. Fault trees, influence diagrams, and Markov models are just a few of the various disciplines used to form conclusions on what factors contribute to risk of adjacent land development, or how factors combine to result in maximum regret, or what emergent conditions disrupt the model of risk, or the time horizon to adjacent land development, and the most effective actions to mitigate the risk. The first model utilized helps determine which factors are the most important. The simplified factor diagram describes relationships between factors and the resulting financial costs and opportunities. Expert elicitation with officials affiliated with transportation planning, economic development, and others allowed for determination of the most relevant factors, an understanding of the relationships between those factors, and the financial costs and opportunities. The objective is mainly influenced by the determined time to development, cost for protection, and the opportunities arising from protection. The next model explored aims to identify what factors contribute to regret. This fault tree shows the factors that can likely cause unprotected land development to occur. The next model provides insight to how scenarios of emergent conditions influence the priorities to avoid risk and regret of land development. In some cases, the relationships between factors change given certain conditions. This study was most focused on the effects of economic fluctuations, such as downturns and upturns, climate change scenarios, and the effects of large-scale developments. This method is being tested on the Virginia statewide mobility system. This large transportation network spans over 5,700 miles, joins 95 counties and 39 independent cities, and neighbors 5 states. This network covers a very geographically diverse area, including the largely urban north, suburban areas, and largely rural areas. The diversity in areas throughout the state cause separate land development patterns to exist between rural, urban, and suburban areas. Factor data is then combined using relationships elicited from experts to quantify likelihoods of land development for each census block adjacent to the studied corridors. The fourth model analyzes the time to development for sections of corridor. Markov models and reliability theory aided in the conversion from the likelihood of development to an estimate of time to development. The fifth model illuminates the options that are available. Costs and benefits are weighed along fixed-length time intervals, in this case 5, 10, and 10-plus year periods. This allows for first-pass decisions to be made regarding prioritization. Prioritization results show darker areas requiring the most prompt action. The outputs of the priorities can then be evaluated by transportation planners to make future funding decisions. However, once initial prioritizations are made, there is much more to be learned. The automated nature of this analysis allows for complex calculations of multiple scenarios to be quickly computed. As expected, many corridor sections show different prioritizations and extreme differences in costs. From a risk viewpoint, these critical scenarios pose the greatest concern and required further study. In summary, 5 major models were used to determine corridors vulnerable to adjacent land development. Applications of the study can be used to aid in land use and zoning, classification of corridors, and other transportation infrastructure such as bike, pedestrian, rail, bus, and air. This effort is critical to avoid the exaggerated costs and impaired service levels due to the need to accommodate adjacent land development along corridors. This effort is and will be a topic of wide interest to SRA members. The Dulles Metro Rail expansion in Northern Virginia is one example of the high costs and inconvenience resulting from the need to retrofit transportation infrastructure in heavily traveled areas. Up to 20% of the $5 billion could have been avoided with the risk-based land use planning. This concludes a brief description of this study. This may be the first time a risk-based approach is being used to forecast land development and prioritize corridors for protection along multiple fixed interval time lengths. This approach is flexible and can accommodate a large variety of data sets. The data-driven methodology allows for objective and large-scale decision-making. The automated structure allows for the model to be easily passed to transportation planners for future updated use and even be transferred online for collaboration between states. This effort has grown my experience and interest for a career in technology consulting and risk analysis. I hope this presentation is of interest across the society, where infrastructure is related to areas such as health and the environment. Thank you for your time.